All right, this is going to serve as a continuation of the previous section, and here we're going to be debugging the code so far. Um, well, we're running the code in debug mode just to check that the v-actual and i-actual variables that were created are actually being updated with the values of the voltage and output current. And that's very important to note before going ahead with the control. First, the first part that has been ascertained is that the duty cycle can be changed. That's great. The second part is that the timer interrupt is being triggered, and that's very important to actually execute the control code. And obviously, the third part is ensuring that we can actually read the output voltage and output current with the equations that have been proposed in the previous section. That everything works out, because those three things are absolutely important to obtaining closed loop control. If one of those is not set, then nothing's going to work, basically. And in this case, we've confirmed the PWM is fine and can be changed, but the other two parts have not been confirmed, and that's essentially what will be demonstrated in this section. So to run this in a mode, so STM32 QBID actually has this great feature called the live expressions in debug mode, but you actually have to set it up, which is as follows. First off, you want to right click on your project, and then you want to scroll down to um, what is it at? I keep losing my way with this. So uh, you want to ensure that you go to your debug configurations first, the debugger, and select the debugger and scroll down to where it states enable live expressions. If this is not stated, you need to set that um, and be done with it. Well, in this case, I'm just going to leave it there as I found it. So obviously I already said it before, and you want to close that. And the next thing you want to do is you actually want to run this here. So this next part you should actually see, go to show view, and you should have live expressions here, but um, it's actually going to show up once you start to debug. So um, you need to click on debug, and of course it's not going to debug if you have errors, so but there are no errors in this case. So once that's done, you say switch to a different perspective. So what you want to do is you want to go to Windows, Show View, and you want to go to Live Expressions. So under Live Expressions, you're going to click on there, and you're going to click on the expressions that you want to see, the actual being one of them, and I actual being the other one. And you're actually going to see them show up as such, the actual and I actual. And in this case, next what you want to do is you actually want to run it. There, resume. So I have a converter here, of course, with the duty cycle of, in this case, it's 400 divided by 849, which is 47%. It's almost 50% duty cycle. So I'm actually going to turn it on, and you're going to see the live readings show up. And there you go, you have the live readings. It's fluctuating quite a bit. Another thing I want to state is in firmware, I find in my experience, with people that are, some people that I show firmware to, it's sort of like, there's usually a huge shock when they see what's been read by the microcontroller. Like in this case, it's fluctuating quite a bit, but not to worry. This, from my experience, from what I've experienced so far, that, um, is not that weird. Ideally, you want to have super stable values, but it's a microcontroller. It's not going to be stable all the time. These are real world readings. It's not always going to be super stable. If you want something more stable, we're dealing in control state. If you want something for a display, then I would suggest extreme averaging. Like averaging, like I'm talking over 1,000 points at least, and then you would have much more stable values. But in this case, we're dealing with control, and we can expect that this will be compensated for in the control. So anyway, what we have here, so that's just a brief overview as to basically not panic when you see readings like this. You can see it's hovering between about 10.8 and 11.4. And of course the current is hovering between 1.42 and 1.45. About it jumps to 1.39 every now and again. But it should be noted that the output impedance in this case is about 7.5. So in that case, it's actually not that weird, the values that we're obtaining here. Anyway, keeping that in mind, I'm actually gonna switch to the oscilloscope view, and I'm gonna show something. I want to show something in this case. Okay, let me just change that. Okay, that's that. Alright, the flash is on. Let me just adjust the camera slightly. It states a reading of 12.4, which is widely different to what is stated on the it's very different to what is stated on the code, on the live expressions view. And I'll tell you reason why, because there's a reason why it looks like that. Specifically, um, the oscilloscope that's being utilized in this case, it's a Chinese brand oscilloscope, and it's not, I don't think it's calibrated that well. So there's a slight difference, a slight offset when it senses these readings. It says 12.4 and it's eerily stable. It's not fluctuating at all. But in actuality, when you use the multimeter on this, which is much more accurate, I would say, in this case, you would actually get a reading of 11.2. And yeah, I'm gonna demonstrate that just now. All right, in this updated view, you can actually see the multimeter reading side by side with the oscilloscope, what's been read on the oscilloscope. So the oscilloscope states 12.5 volts, whilst the multimeter actually shows a reading of 11.48 volts, which is a more accurate reading to sort of show that in the further examples, you should just understand that the oscilloscope on average adds 1 volt to the readings for whatever reason. It just kind of does that. And yeah, might be a slight offset issue, but it's just something to take note of. Especially working with this experiment, with this specific scenario example, rather. Let's see, I'm gonna take it away and bring it back to sort of show that in this case, yeah, what is actually going on with the oscilloscope reading and the actual reading. Yeah, so I'm gonna switch back to the view of the firmware. So basically, as you can see, the values are still updating. It says 11.48, which I would say on average might be the value slightly lower than that has been read. Um, I wouldn't worry too much about the offset that I'm seeing here. Most importantly, it's in the ballpark range. I am sampling every 100 microseconds. I expect it to sort of sort this out later on. Of course, in the control sort of fixes a lot of things. I don't know if that's one of the feature of general compensated, but anyway, I sort of don't want to ramble on and on about these readings. The most important part is you are able to actually view your system, view the output voltage and output current of your system using live expressions. that's provided by the STM32 IDE, and actually set this up properly to view them. And that's about it for this section in terms of initializing it. In the next section, we'll obviously be diving deeper into the control. It will all still within the firmware, but in this case, in this the next section, I'll sort of be making different folders, different files rather, to sort of organize them better. So that's about it. So before in your application, you shouldn't close it here because you're not sure what it might default to. It might default to 100% duty cycle. So what you want to do is you want to turn everything off first. Make sure you have 0 volts in the output, and then you can turn it off there. And then you should be sorted. Alright, that's about it for this section. I'll see you in the next one. Cheers.